Hello, everyone, and welcome back to the virtual stage. Next up, we have a really exciting presenter. We have Patrick Miller, and he's the lead of enterprise of the ML team at Google. And today his talk is entitled The Machine Learning Project, Lifecycle in Google's Enterprise. So please welcome to our virtual stage, Patrick Miller. Patrick, you can come on up. Great. And I will just close out my video. And when you're ready to start with your slides, you can go for it.
Great. Thank you, Morgan. All right. Hi, everyone. I'm Patrick Miller, and today I'll be taking you through how my team at Google approaches a machine learning project from start to finish. I've been putting machine learning solutions into production for almost 10 years now, the last 2 of which I've spent helping Google expand its own usage of AI in the enterprise. Over the past 2 years, my team has launched dozens of different models and driven tens of millions of dollars of annual impact through making the business more efficient and effective. Before we jump into how we go about doing that, I want to go over a little bit about what our group looks like. So Google has many AI-first products. You may have heard of some of them. You have Search, Gmail, YouTube, Android. We don't work on any of those. Instead, my team is tasked with helping run Google the business with that same AI-first mentality. We bridge the gap between Google's 5,000 plus ML researchers and Core Bench, Google's enterprise engineering organization of about 3,000, which supports every Google function from legal to marketing to HR. We do a lot of consulting, mentoring, education, and we also do a bunch of implementation ourselves of ML solutions to fit into Core Bench's products. The enterprise AI team is 16 people right now, with a couple site leads and a product manager. I run the NYC team with 10 engineers, and we also have a team based out of Austin. All in total, we work on about 15 engagements at a time, one of which I'll be using today as an example. We partner with business leaders and other engineering teams to make sure our AI solutions drive as much value as they can. One of the groups that we work often with is TechStop, our IT engineering and tech support team. So Google's IT landscape is unique, but in many ways it shares the same problems that any business does. Googlers file millions of support tickets every year, asking for help on anything from installing new software to remoting into their machines. As you can imagine, many of these problems come up over and over again. So a team in TechStop has created thousands of support articles to help with solving some of these issues. The articles are searchable, but there's so many of them that oftentimes Googlers just ignore their availability. Our partner team in TechStop, dubbed the self-service automation team, has as part of their mission the goal to increase adoption of these sorts of self-help mechanisms. In collaboration with them, we identified this as a great use case for machine learning, where we can take in a normal support ticket and automatically retrieve an article that solves the end user's problem. With the stage now set, let's jump into the meat of this presentation. I've been using this framework for about 6 years now, and it's proven to be pretty successful at actually getting machine learning into your business and driving value. I call it the ML project lifecycle. I know, very creative name. It grew out of a need to add a bit of process to a field that can feel a bit exploratory and experimental at times. I haven't had much success working in ML with traditional process methodologies like Scrum, but still wanted to have some structure that allowed my teams to be agile and move things forward in a product-focused fashion. So this is how we manage those 15 or so projects at a time. It allows me to keep track of all of our work and focus our attention on areas that present the most risks. The stages in the ML project lifecycle themselves aren't that revolutionary. We start with an ideation phase where we do the typical product manager routine of identifying the problem, stating the business value, and framing that problem in machine learning terms. Next, we move on to acquiring data. Data is the lifeblood of any machine learning project. So we focus on listing out which data sets we need and which data sets we already have so that we can go out and acquire new ones if we need to. After that, we move on to some cycles on data exploration. Here, we really dig into the data and get an understanding of the domain that we are working in. We craft our features and create the response variables that we want to predict. Next, we get into everyone's favorite part, the model prototyping. This is where we get to try out all of those cutting-edge machine learning techniques that you've been hearing about at this conference. We make sure to tie those models back to the business impact that we are trying to drive and validate that performance we are seeing is adequate with demos to our business stakeholders. And once we've finally settled on a model that is performant, we move on to putting that model into production. We ensure that we have all of the needed tests in place and verify that the model performs as well in the wild as it does on our historical data. And finally, we bucket some time to monitor how the model changes over time and report back the impact it has had to our leadership. With this framework, we can take on many projects at once and evaluate their merits against how much work we think the different stages will take for each of them. All right, so how did we settle on this tech stop article suggestion project, and how do we kick things off? As with any project, we start with an assessment of its potential impact as well as its fit for machine learning. Working with the self-service automation team, we came up with 3 potential ideas for leveraging machine learning to help with tech support at Google. First, diverting traffic away from field technicians by surfacing relevant support articles. Detecting trends in support tickets to solve the next big problems in tech support. And third, finding anomalies in machine logs to help users before they file tickets. We take all these projects, we compare the impact and complexity of each of them, and we also compare them across our entire portfolio. So we're comparing these projects against HR, legal, marketing projects as well. And after we complete this analysis, we settle on the portfolio of projects we're going to work on. And so we ended up settling on support article suggestion as one of those projects. We came to that conclusion because even with a relatively poor performing model, we would still gain tens of thousands of hours in efficiency. So it clearly had the impact. It also checked all the boxes for a good machine learning project. There's a lot of data. We want to make a bunch of automated decisions. Retrieval problems and natural language processing fall into the realm of solved problems. And we can easily tie model performance to how much money we will save. When I say tie model performance to real world impact, this is what I mean. We work with our partner teams and product manager to understand what drives business value and literally tie it back to the recall and precision of the model. That way, we have a strong understanding of what type of model performance we need to hit in order to have a high ROI project. So we've completed ideation and problem framing. Our initial thought is to treat this as a retrieval problem where we have some text and we want to retrieve something from a knowledge base that most closely matches that text. The next step in the ML project lifecycle is data acquisition. This first includes an inventory of all the data that we currently have access to, as well as listing out the data sources that we want but currently are missing. On the knowledge base side, we have simple access to every support article that we want to surface to the user. These are articles on installing new software or debugging login issues. On the ticket side, we also have ready access to millions of historically solved tickets. And in these tickets, a TechStop field technician often includes a URL that links out to a relevant support article. In this example below, a Googler filed a ticket about a problem related to getting access to their machine via the SSH. This Googler may or may not have been me. When the TechStop technician reviewed the ticket, they manually linked to an article about common SSH issues, which led to solving the problem. About 10% of all these tickets contain a URL sent from a field technician that matches a support article. We can use this data as our training data. While it isn't ideal or the cleanest, we believe it is sufficient to get started on a model. But before jumping straight into modeling, we do a little bit of data exploration to understand the domain and the data we are dealing with a bit better. This is where you spin up your Jupyter Notebook or Colab and start looking at the data in detail. Things in the support article use case that we wanted to check out were the completeness of our features. Do all tickets have both titles and descriptions? Are there any peculiarities with the ticket data? How useful are each of the articles? How often does each article get referenced in the ticket corpus? You can see that distribution here on the right, which follows a power law distribution. A few of the articles solve most of the problems. Okay, now that we have a handle on our data a bit better, it's time to jump into the next stage for some model prototyping. I mentioned earlier that we had framed this problem as a retrieval one. We receive inquiries from Googlers, and we want to look up the best answers to solve their issues. This is a pretty well-known problem in machine learning, and a very common solution to it is a dual encoder or a two-tower model. These model architectures are used to encode both different types of text documents. We have an encoding for the question, or the ticket in this case, as well as an encoding for the answer, which is, in our case here, our articles. Using a similarity function, such as cosine distance, we're able to compare these two encodings in the same embedding space. That means that for any new ticket, we can look up the closest article in that embedding space. Compare this to a more naive approach in the QA example, where whenever we get a new question, we have to look up a question that is textually similar. For shorter form text, this can be problematic because there sometimes just isn't enough meat there to understand the similarity in semantics between differently worded questions. It also means that we can't leverage those question-answer pairs that we have already labeled as effectively. With a two-tower setup, we get the benefit of leveraging the richness of our articles. Okay, so we can build our two-tower model using encoding for both the ticket and the article. As with any machine learning project, it pays to start simple. So we first use TF-IDF for the encoding of both the ticket and the article. Then we move on to word embeddings for each. And after that, we try some contextual language models, such as attention-based ones. After each, we record our performance and, oh, well, it doesn't look so good. Uh-oh, what's happened? We have several questions we ask ourselves when we run into performance problems at this stage of the ML project lifecycle. For example, do I not have the right features? Or do I have significant room for model experimentation? Did I frame the problem incorrectly? Maybe that one's it. Wait. Didn't we do problem framing like 3 steps ago? We did. But this is something that is totally expected in a machine learning project, something you should expect in almost any single one of your own projects. Things don't always work out perfectly, and you need to be able to be quick to revisit steps earlier in the process when you need to. I mentioned scenarios where you just don't have the right features to solve your problem. In that case, you jump back to data exploration and create them. For us, we have pretty clear-cut features. However, I do think we have a bit of a problem framing issue. So let's jump back to the ideation phase and run through it one more time. A very common mistake in machine learning is to start with the solution before the problem framing is fully complete. While it is tempting to get into the weeds, it really does pay to spend some time understanding the problem first. And starting from the impact really helps. Remember that table of recall and precision versus hours saved? Well, if we focus our attention on that, does it matter at all which particular articles we are suggesting, as long as they are correct and we suggest them frequently enough? It doesn't matter at all. And if we remember some of that data exploration, we learned that there are a bunch of articles that only solve a few tickets. If we toss those articles completely out, we might be able to focus on the highest impact articles and come up with a model that performs better. And while we're at it, can we simplify the problem? With many fewer classes, we might not need this sort of deep retrieval architecture, and instead can try out a simple multi-class classification. This allows us to add in another element that we were missing before, which is a large swath of tickets without any article that solved the problem. Our refined objective should be to return the most sought after articles only when they make sense, and return no article if there isn't a good fit. Okay, so we make it back to the model prototyping phase. Once again, we start with a simple model to act as a kind of baseline. We use TF-IDF encoding for the tickets. Remember now that we aren't using the dual encoder setup, and we have our articles as our classes, so we can't really encode the text in them as features anymore. After we get our TF-IDF baseline set up, we move on to word embeddings in a simple contextual embeddings model using CNNs. Our performance, okay, so it's better, but not exactly world-beating. Precision of 50%, which is only okay, and recall of 25%, which is on the lower end of our targets. We wouldn't really be driving enough impact to launch this model into production. So let's perform the exercise that we did before. Are we missing features? It still seems like we are fine there. Have we done enough experimentation? Well, we're closer to our targets compared to last time, so maybe we can get better performance with some stronger models. However, at this point, we've run several experiments with different setups, and talking through it, I'm personally already a bit lost. It's clear we need a better way of running these experiments than in Colab. Enter XManager, an experiment management platform developed by DeepMind. It makes launching experiments and tracking what we've tweaked very easy. It allows us to more seamlessly use all those TPUs that Google has, and it allows us to run a bunch of these experiments simultaneously. So thank you, DeepMind. So what are we going to do with our newfound horsepower? Enter BERT, a now maybe not so state-of-the-art language model that is nonetheless extremely powerful at understanding context in natural language. We have access to BERT pre-trained on several different data sets. We can use those embeddings directly on our own data set and learn on top of it with our class labels. With a little bit of engineering, we can get this set up to run on our TPUs, and we're off to the races. Results? Well, better, but on the low end of our targets. Can we do more? Luckily, we have access to all of Google research, and we quickly learned that using BERT often works best when you do a bit of fine-tuning using the BERT training tasks, namely the masked word training task and the next sentence prediction training task. If you aren't familiar with how this works, I totally recommend going and reading that paper. It does a great job at explaining how modern-day attention-based language models work. So with a little bit more of engineering effort, we can massage those tasks into our use case, and the result is, well, still not the improvement we were quite looking for. All right. At this point, some of us were getting a bit disheartened. We were due for a check-in with our partner team, so we decided to use the opportunity to both show our progress and also get some input on the latest results. So what we did was we set up a demo to debug the output of our model. After going through some of the correct classifications with the self-service automation team, we also showed our partners some of the mistakes. Our first example was a Googler asking for help with out-of-office notifications. The model tried to link an article about Microsoft Office, while the support technician didn't include any article in their resolution. Clearly a mistake in our model. Having some technical difficulties here. Sorry about that. All right, starting back. Our first example was a Googler asking for help with out-of-office notifications. The model tried to link an article about Microsoft Office, while the support technician didn't include any article in their resolution. That's clearly a mistake in our model. Our next example was a Googler asking for help setting up monitors. The model said an article about choosing the correct cables would help, while the support technician didn't include any article in their resolution. This seems like a more reasonable article to suggest, but the details of the ticket didn't really have much to do with cables. Our next example was a Googler asking for help with machine certificates. The model proposed a detailed article about installing certificates, while the support technician didn't include any article in their resolution. We reviewed both the ticket and the article with the TechStop folks, and they agreed that the article would have solved the Googler's problem. Okay, so an error in our data. Let's look at another one. Googler wants to set up a privileged access for their personal Nexus. Model proposes an article for setting up your account on your personal Android. The support technician didn't include any article in their resolution. And at this point, we realized that we had a problem with some of our labels. TechStop agents don't always send an article along with their resolution, even when it would help. Yes, I'm sure all of you are thinking it's time to revisit some of those previous stages. And you probably already know which ones to go back to. We have a problem with some of our data, so let's go back to the phase where we collect the data. What are we missing exactly? Our data is underlabeled, leading to model metrics that could be misleading. And if our data is severely underlabeled, our model might be learning the wrong things. First things first, though, we don't have a great understanding of exactly how well our models are performing. So one way to fix that problem is to create a golden evaluation set with validated examples. So this is what we set out to create. We had a group of TechStop agents hand label 2,000 tickets for us, a mix of tickets linked to different articles as well as a large chunk of tickets that really didn't have any article that solved the problem. This golden set more closely reflects the reality of a workflow that uses our model. If an article solves the ticket, our model should return it. And with the golden set, we can go back to model prototyping and get a clear evaluation of how our models are doing. Or with X Manager, we can track the performance of all of our models against that golden set at once. And here's some of the experiments. I'm showing you these particular ones pegged at 80% precision so that we can compare recall across the different setups. You'll notice that our metrics are much higher than the ones we showed previously. The golden set really helped us out here. Our BERT models are the winners, and particularly the BERT model with the pre-training task does the best at 43% recall. There's definitely more room for improvement here. I still think we could get some of these performance metrics for the two-tower model up. But one thing that we emphasize with the ML project lifecycle framework is making sure you hit your goals and move forward to production. You can get stuck in a rabbit hole of over-optimizing when clear value is already on the table. We can always revisit the model later on. On to our next stage, model productionization. An ML project in production doesn't just consist of our ML code. There's also a whole slew of other software that you need to build around it in order to avoid the many pitfalls and tech debt that comes with an ML production system. Luckily, Google has already developed many platforms for making this much simpler than it was 5 years ago. We use TensorFlow Extended, or TFX, for handling most of this productionization. And we push to a managed API platform, Servomatic, for serving so that we don't have to worry ourselves about scaling and SLOs and all that other fun distributed engineering stuff. In this phase, we want to make sure that the results that we see in prototyping line up with those in the real world. The golden set that we created really made this process smooth for us, and we didn't end up seeing much slippage at all. This also gets handled by TFX just straight out of the box. So what is TFX, you ask? Well, here's what our full TFX pipeline looks like once we have deployed to production. TFX handles everything end to end. So it creates examples for you. It generates statistics on the data to make sure the data isn't changing too much over time. It's where we put our feature engineering so that we don't have any training serving skew. We have a bunch of validators on top of our model here to make sure our infrastructure doesn't change without us knowing, and to make sure our model's performance still hits a particular threshold. And TFX handles pushing the model when new data comes in to Servomatic. With our model in production, we move on to the final stage of the ML project lifecycle, which is monitoring and maintenance. There can be a whole presentation on managing tech debt in an ML project, but I'll do a quick overview. The main things we're looking for are, how does our data change? How does our model change? And does the model create any sort of feedback loop? So how are we training the model on data that has been produced by the model? Are we having TechStop agents continue to provide feedback for us? If we did the previous phase well and used TFX, there isn't really too much work to be done up front here. It's just a matter of monitoring our TFX pipeline's output and responding accordingly when we need to. As I said last section, TFX does this for us. And so that we've launched and we're in production. Hooray. Let's quickly recap and discuss some other considerations. First, take a structured approach to your machine learning projects, like the ML project lifecycle. It will help make sure you don't get stuck in endless research and never get to actually deriving value. However, because of the nature of ML, be ready to iterate and go back to earlier stages. For each of the stages, be able to answer the question of what tools should I be using here. Starting in a notebook is great for early exploration, but make sure you also have tools for scaling up your experimentation and then also productionizing your model. And finally, getting off to a good start is very important. Make sure you are working on problems that are actually impactful and are good fits for machine learning. Before I sign off, I wanted to share a last consideration that our team is taking to heart more often when starting out projects. AutoML was an area I was skeptical about for a while, but I've seen it work out now in practice at Google multiple times. It currently only fits with certain problem types, but it can handle cases like text classification pretty effectively. The AutoML tool we use internally is called AutoTFX, and is added benefit of allowing you to export the TFX pipeline and significantly expedite the ML project lifecycle. It allows us to really leverage the domain expertise of our partner teams and to focus on some of the most critical work in the ML project lifecycle, namely problem framing and configuring the production setup, both areas where ML expertise is especially important. With that, I'd like to thank you all for joining me today and listening in on how we handle machine learning in the enterprise at Google.
That was great, Patrick. Thank you so much. You can unshare your slides. Thank you so much for sharing with us today. And I hope you all enjoyed. Stick around for the next session or a one-on-one networking session.